Okay. Yeah, thank you for the invitation to speak, and thank you to the organizers. Yeah, I'm going to talk about something that I'm calling homotopy path algebras. So I just erased the title so I could fill it in. It's kind of hard to spell going downwards, but okay. And then I added to the title this and resolutions. So meaning like projective resolutions of modules. So that's what I'm going to talk about today. So I'll tell you what these things are. But I wanted to start with some examples, maybe some being two. All right. Okay. And so I'm going to start with a polynomial ring. So I'll start with a polynomial ring. K. So K is some field, and I have a polynomial ring and n variables. And that comes equipped with a Zn grading. And if M is a subgroup of Zn, then I can just pass to the quotient grading. So I maybe think of this as a multi-grading or something like this. Or, possibly, for example, MM is the subgroup generated by EI minus EJ, and you get the standard 1, 1, 1, 1, 1 grading on polynomial ring. So okay, so I want to ask myself the following question. If I give you a finitely generated projective graded S module, so S is this polynomial, I should have said S is this polynomial ring, okay? So let's call that module P. How do I describe the endomorphism algebra of that P? So N P. Let me put Hom PP in degree 0 is what I mean. Okay, so endomorphisms as graded modules. So this is, this is by definition the sum over ij. So if P is sum of, okay, I'll put it there. So S j minus I. Let me squeeze in one more thing. So P is a projective module. This is just going to be some sum of S of I. I'm looking at the wrong page in my notes. So here I just want to put as graded S modules of PP, which is S PP. Okay. That's all I want to say here. And then I wanted to give an example. So that's just my question. Okay. So now I want to explain in an example. So I'm going to take the standard grading on a polynomial ring in 3 variables. And I'm going to have P be S, S of 1, and S of 2. Okay. So P is just this projective module, which is a sum of 3 free summations with these twists. So I'm going to get the sum over ij from 0 to 2 of Hom from S of I to S of j, which is the sum. So I'm just gonna, this term is really just the degree j minus I part of this ring. And in this case, this ring is positively graded. So I can actually, these will be 0 unless j is greater than or equal to I. Okay. All right, so that's kind of still abstract. So can we do a little better? Okay, well, I could think of this as, well, this is the endomorphism ring of a of a free module of rank 3. So I can think of this as matrices, 3x3 matrices with values in S. But since I took the degree 0 part, what I'm going to get is a matrix where these entries have to be linear, and this entry would have to be quadratic. Okay, so some subalgebra of this matrix algebra, that's another description. And now I want to do more of like a quiver type description. Okay. So I'm thinking of I'm going to think of this as a topological description, and that's going to be my goal for the remainder of this talk. Okay. So if I draw these three summands, S of 1, and S of 2, then I'm going to think about maps between them. Well, the maps were only going in this direction because this ring was positively graded. Okay. And I've drawn 3 arrows here representing the 3 possible linear monomials from S to S of 1. So these arrows are really X, Y, and Z. And this, or you can think of it as the linear, it's a basis for the linear part of this ring. And here it's just repeating. And here I would have quadratic terms, but it so happens that in this example, all quadratic terms are combinations of the linear terms. Okay. So this thing is called the Bailenson quiver. So now I've just drawn it a little simpler. And I'm going to denote by KQ all K linear combinations of paths in Q. So it's just a finite dimensional Q vector space right now. So I have this trivial path here, this 3 trivial paths, right? Then I have these paths, X, Y, and Z, or these paths, X, Y, and Z. But I could also do stuff like X times that. I can combine these 2 paths. I can take this total path along these directed arrows, XX, XY, XZ, or I can do them in some other order. Okay, that's KQ. But this doesn't quite, this is larger than the dimension of this endomorphism algebra. Okay. And so, sorry, the next thing I want to do on KQ is define multiplication. So this is a ring. red and black. This is a ring under concatenation of paths. So I just put an example here. So I could do x times x, and I'll get something, this element, which I called the path x times x. But if I tried to do this x and then this path, I can't concatenate those. So I just define it as to be 0. Okay, so this is certainly a non-commutative ring. These don't commute. All right. So now, if I wanted to describe this endomorphism algebra of P, I'm going to take this quiver, but I need to introduce the relation that in my endomorphism algebra, the monomial, which was the degree 2 thing, right, called x times y, was the same as the degree 2 thing called y times x. So I introduced that relation, and I also need that for of course, all of the monomials. So if I take this, all linear combinations of paths, and I quotient by this ideal, I'm going to recover this. And now this I want to think as a topological description of this algebra. Okay? So that's what I'm going to make precise for the rest of the talk. And I'm going to see if we can get some mileage from that. Okay? So I have one more example. Just quickly. So if I had graded this with degrees 1, 1, and 2, and taken this to be my projective module, I'm not really letting you know why at the moment, okay? But then I would get 4 vertices corresponding to the 4 summands. And now I have only 2 linear terms, but z is a new quadratic term. Well, sorry, maybe that's not good terminology. It's a degree 2 term, so it's jumping. And I still get these kinds of relations. Okay, any questions? So now I'm ready to begin with what's a homotopy path algebra. So I want to start with, I have 3 different definitions of this thing that I'm going to give you. Okay, so I'm going to let Q, so this kind of thing I want to call a quiver, just going to be some kind of directed graph. So I'm going to let Q be a quiver, and I'm going to consider now an embedding of that quiver into some topological space X. Okay. And I want to define a homotopy path algebra it's going to be this algebra KQ, or the algebra of K linear combinations of directed paths in Q, okay? But up to path homotopy in X. So let me make that slightly more mathematically precise, right? So I have this, I have some field, some base field, even it could be a base commutative ring. And I have an algebra, and I have an embedding of Q into X. And now I want to define an ideal. Well, I'm just going to define the ideal P minus Q such that P is path homotopic to Q. Okay. And I'm going to define the algebra, the homotopy path algebra, to be KQ mod I. Okay. So, for example, if this is my topological space, it's a closed disk, right? then this path is homotopic to this path. And so KQ here is, so the algebra would be KQ mod this single relation, AB minus CB. Okay. Questions? Okay. That's it. That's either good or bad. We'll see. So here's another example. So this space is a torus. This is on a torus, and it's the same example, right? But I want to think of it on a torus. So I'm going to draw on the torus. I'm going to draw the first vertex here. The second vertex is drawn 4 times, right, on this torus. The third vertex is somewhere here. Okay. So going out, I have these paths x, y, z, x, y, z. So these are the same thing, right? This is just it. I've embedded it in this torus. Okay. And so now you see that if I took x and then y, or y and then x, well, that's this path here, right? So this disk is here, so these are homotopic, and I get this relation. And similarly, well, if I went out from x, then this purple point is repeated here, and I have this disk here, which is here, which gives me this relation, okay, and so forth. Okay, so another way to describe this algebra is I embed, or the endomorphism algebra of that original projective module is I embed this quiver into this torus, and I take its I take the paths up to path homotopy. So let's make that a
Can I
definition.
just ask?
Yeah.
What different result we would get by embedding it into like a plane or something? Or so in particular, where are the cycles of the torus?
Yeah, so we could get a completely
which relations
different...
would that not be?
Right. So we would get... Okay, that's a great question. Let me give you
Well,
let me give you... So okay, so first of all, maybe x in a plane, this x would equal this y, and so you would just get this picture in that example. Okay. And what I would say is actually you can take, if you think about this as a category, you can take the nerve of this category, and this picture embeds in the nerve of this category. So there's something canonical you can do, okay? And if you do that, sorry, if I started with the if I started with the relations, okay, then I could think about the nerve of that category with the relations. If I take that, I'm going to get a canonical space X to embed this in that will recover the relations. Okay. Mm-hmm. So in some sense, there's something forced. Let me keep going, and I think things will become more clear.
Okay, thank you.
Okay. Okay, so now I'm gonna get, I think maybe this is maybe the type of description you're asking for. So this is the purely algebraic description. So rather than have an ambient topological space, I can just give you a algebraic description. And maybe I should have started with that. Maybe you would have preferred it. I don't know. So A is just an algebra KQ mod I, where I is of the form P minus Q, is generated by paths P minus Q for some set of paths with the same starting and ending point. That's forced if you want them to be path homotopic, right? And also, a path homotopy is cancellative in the fundamental groupoid, right? So if you had x times p minus q and I, then p minus q should be an I. And I think I omitted that it should be right cancellative as well. Okay, so it's left and right cancellative, which is just forced by fundamental relations in the fundamental groupoid. Okay. So I could start with this and ask, and I could ask myself, well, are these two are they the same definition, right? Well, it's not hard to do. So can I, if I just give you an abstract algebra like this, how would I build a topological space X? Well, for each p minus q in I, just glue a disk to, so you can think of the quiver Q as a graph, as a topological space, and just glue a disk with boundary PQ inverse to it. So there's a topological space that will give it to you, but I'm omitting this from my talk today, but there's something more canonical you can do, which is more canonically take the nerve of the path category. So there's a more canonical topological space which has much more better properties with respect to how this algebra behaves. But
this nerve, you mean you view it as a simplicial set and then take its topological realization, or?
That's right. Yeah.
Yeah. Okay.
So yeah. Yeah. If you have other questions about that, I have lots to say about that, but I'm not going to say anything about it. Okay. Okay. So I want to get to a third definition, which is via stratifications and exit paths. So let me tell you what I mean by that. So I can also view these algebras as coming from stratified topological spaces. So let I be a poset. And then there's a technicality here that you can give I a topology. If you have a poset, partially ordered set, you can give it a topology where the basis of opens is just the upwardly closed sets. It's called the Alexandrov topology. So it has some topology. I'm not going to get too technical with that. I'm not going to try and understand it that well in this talk. But I'm going to give you it's just a formal way of encoding what I want to say about this. So stratification is just a nice way to think of a stratification. Is it just then, if you give a poset this topology, a stratification is just a continuous map from X to this poset. Okay? And what do I mean by that? Well, if I have a continuous map to some, you can think of this as some finite poset, let's say, right? Well, actually, in the next example, it won't be finite, but right, whatever. So the level sets are just the strata are just the level sets of this map. So I'm going to write it as a set theoretic disjoint union. Of course, topologically, it's not, but set theoretically, it's a disjoint union of its level sets. And so we'll call these level sets SI. These are the strata. Okay. And so making this a poset has something to do with how these strata interact. Okay. So let me explain in an example. So if X is Rn, and my poset is just Z to the N, with its usual ordering, okay? It's just a partial order, like you have to be, the difference has to be strictly positive, the difference has to be non-negative in every term. So then what's this map? This map is the floor map, okay? And this map is, you know, this doesn't have the discrete topology, right? This has this poset topology, and this floor map is continuous, okay? And the strata are then just the cubes, these half-open cubes, okay? Because I feel that they're drawn. I think this is the ceiling map, the way I drew these cubes. I think these cubes should probably be drawn like this. Let's call it. Okay. I'm gonna redraw my cubes. So I'm stratifying R2 with these cubes. Okay, and I'll call this the cube stratification. So Rn would be, of course, not topologically, but as a set, it's the disjoint union of these cubes. Okay. So some good things about stratifications. Oh, sorry, first an example. So X could just be some regular CW complex, then I could be the cell poset of X. So for example, if X is a triangle, I is this poset. The Hesse diagram looks like this. Okay. So a CW complex is a nice stratified topological space, stratified by its cell poset. And some remarks is that if I have a map of posets, right? So if I start with a stratified topological space and I have a map of posets, I get a new stratified topological space by just composing. Or if I started with a continuous map X to Y and X was again a stratified topological space, I get a new stratification of Y by just composing, right? So for example, if Y is, say, some kind of subset of X, then strata are intersections. Okay. So let's do this with our cube stratification. Okay. So now let's let M be a subgroup of Zn. So I'm going to think of MR, meaning I'm tensoring this M with R, and I'm getting some vector space in Rn, okay? And then I had this floor map. I added a negative sign based on some convention, okay? And that, oh, maybe my cubes were drawn correctly because of this negative sign. Anyway, and then I'm going to add this quotient map mu to Zn mod M. Okay, so what I just told you is I started with some stratification, some stratified topological space. I could add in any continuous map here, and I could add in any map of posets here. Okay, and so now I get this new stratification. So for example, if I do R3, and I take this lattice, this subgroup of R3 generated by these columns, okay? Then I take the map 1, 1, 1 here. So this was again this M is quotienting by EI equals EJ, which is represented by these columns. Okay. Then I would get this map. So AB is going to ultimately go to negative the floor of A, the floor of B, plus the floor of negative A minus B. Okay. All right, so I'm just calculating what this thing is, and I've just maybe put in some random stuff. Let's see what comes out. All right. Okay, so here again was the map. AB goes to this thing. So if AB is in the lattice, right? Then this is A, B, and negative A minus B. So this I get 0. Okay. Now if A, so I can think about this. So I get the same value if I add some point in the lattice, right? So I can think of this on the torus, R2 mod Z2, which I'm picturing as this lattice point. And then there's this region here. And then there's this region here. Okay. And so on this torus, if AB is in this region, I actually get 1. You could check that. And then if AB is in this region up here, I get 2. Okay. So the image of this map is actually just the set 0, 1, 2. I don't hit all of Z. Okay. And and so the post set I get is the post set 0, 1, 2, right? Oh, okay. I think if I added this negative sign, I should have put negatives, and the post set should be directed this way. Can I change that? With this, I feel like I missed this negative sign. Okay. And now this post set is going this way. Okay. Okay. So I got this stratification of the torus this way. So I wanna talk about what I can now how to form an algebra from these stratified spaces. Okay. So let's start with some stratification. Okay. I want to define an exit path. It's just going to be a path in my topological space. Such that the composition of this path, right? So the path, if you think of it as a path in I, it's a map of post sets. Okay, so it's directed in this topological space. Let me explain with an example. Maybe it's the same example. Okay, so so we just stratified this torus with these 3 strata, right? This is notation for this. You could think this is MR by M is S1 plus S1. Okay. And these were the 3 strata. And I want to change the signs here. I'm gonna cheat. Okay. And okay. So now to be an exit path means I have a path in this topological space, but the corresponding map, so if this one's labeled by a -2 and this one's labeled by a -1, has to be a map of posets. So this path has to pass from -2 to -1. And paths from -1 have to pass to 0. Okay? So I can look at the exit paths in this stratified topological space. And what I'm getting again is this picture. Okay? So, right. So this picture is the exit algebra of this topological space. So just encoded in this thing with the Alexandrov topology, and what you can just think about it as this open boundary has to pass to a closed boundary. So that's what these exit paths end up being. And now I'm in a topological space and I have a quiver, so I can consider these exit paths up to path homotopy, and I get this homotopy path algebra. So I'm going to give you a definition 3. A homotopy path algebra is the exit algebra up to homotopy of a stratified topological space. Okay. We had this example, and this is an equivalent definition. I kind of mumbled it under my breath, which is one way you can achieve this is you take the classifying space, so the simplicial complex corresponding to the nerve of this category, and you take the exit algebra that comes with the stratification, which we call this tree stratification. And you take the exit algebra of that, you'll recover this algebra. So there's always a stratified topological space that gives you this. Okay. Or I could go back to this CW complex, right? So for example, a triangle, right? I could take the cell poset, and if now these are actually exit paths, and I'm taking them up to homotopy, I get the incidence algebra of this poset, of the CW poset. All right. So I want to now, this story is somehow related to algebraic geometry and mirror symmetry. So I want to start with the following theorem, which was, so for what we needed in mirror symmetry, we proved some version of this for refinements of CW stratifications, like the one I drew for you, right? So if I look at this stratification here, it's not a CW stratification, but it's the union of a bunch of CW cells, right? So there is a CW stratification, which this is a coarsening of. Did I put refinement in? Oops. Let's replace the word refinement by coarsening. So in the general literature, something like this was known for what were called conical stratifications, which, for example, were CW stratifications, but we needed these coarsenings were the types of stratifications we had, right? So Jesse Wang and I proved some version of this for coarsenings of these stratifications, but it was generalized to coarsenings of conical stratifications by Hain, Porta, and Tessier. And so the statement is the stock functor induces an equivalence of categories between constructible sheaves on this stratified topological space and this homotopy path and modules over this homotopy path. Okay, so I'm gonna explain that a little bit with a picture. Oh no, I'm not. Sorry, I decided to delete that. So I'm just going to leave that for a moment now. And I'm going to talk about the relationship to mirror symmetry. Okay. And toric varieties. So let's say I have a bunch of line bundles, L1 through LT, on a toric variety. So the thing I want to study, which I gave you sort of an example of, is the endomorphism algebra of the set of line bundles, of this collection of line bundles. So the first proposition is that this is a homotopy path algebra. So I can study it topologically. So roughly the proof is that the vertices are the line bundles and the arrows are monomials of degree Li minus Lj. So the real context is you can think of these Li, these correspond to put S of V, where V is in some Z to the N mod M. Okay. Maybe VI. I equals 1 to 2. Okay, so it's exactly the context of the initial example. S is, if I give you a toric variety, like projective two space or something like that, then S is the coordinate ring of that toric variety, K join X, Y, Z. And I take some, that comes with some multi-grading on that coordinate ring. And I can take some projective modules and consider their endomorphism algebra. Okay, so these kinds of endomorphism algebras we started with is really what I'm talking about, but now I want to talk about it slightly in this context of algebraic geometry. Okay. So this also comes with the stratification. So I don't know what the familiarity here is with toric geometry, but if you have a toric variety, it comes with this exact sequence. And you can define the image of this map. So you can look at the image of the set of cubes. Of the unit cube at 0. And look at the endomorphism algebra of the sum of all things in that unit cube at 0. And this is called, I will call this the bundle Thompson homotopy path algebra. Okay, so there's a special homotopy path algebra associated to any toric variety. Okay, so this is just coming from convex geometry. I get this associated to a toric variety, I get some exact sequence. I look at the unit cube in Rn, this is some number n. And I look at its image, I get some finite set, which I can view as a poset. There's an ordering by effective divisors on this. So I get some finite poset, and I also can take the endomorphism algebra of the associated line bundles on this toric variety, and I'll get an HPA. So now I want to tell you how that corresponds to stratified topological space. Okay, so I take this torus, MR by M. I don't know, M is a lattice. M is a lattice in some Z in some big free lattice, okay? I can get a torus MR by M, okay? This is just isomorphic to R to the sigma of 1 by some Z to the N. Sorry, R to the N by Z to the N, where N is the dimension of this lattice. And I get strata by taking the pre-image and intersecting with this cube. So I'm just doing what I did before, which is I took this exact sequence. I stratified R to the sigma of 1 with its cube stratification. And then I intersected that with MR. So really, and then I intersected that with MR, and I got a stratification of a torus MR by M. And then rather than stratify it with Z to the sigma of 1, I used this map mu to stratify it with this. But I only needed to take the image P. Okay. So I get some finite poset which stratifies this torus. And I'm going to call that the bundle Thompson stratification. And let me just remind you, so we got that from maps by the negative of the flooring map to Z to the N, and then I mapped by mu to the class group of this torus. So I'm stratifying this torus using this sequence of maps. And this is just the cube stratification at this level. Okay. So associated to some toric variety, there's always a stratification of a torus. I have 10 more minutes, or am I supposed to end? Yeah, okay. Okay. So here's the following theorem. Is that if you start with any toric variety and you take this collection of line bundles, well, it's not true if you know about tilting that this is a tilting object. That is not true. And in fact, there's higher x's between these line bundles. Okay. Nevertheless, you can consider the functor Rhom, and it takes you from the derived category of this toric variety and lands you in the derived category of this homotopy path algebra. And the statement is that this is fully faithful. So in particular, all sheaves on this toric variety can be thought of as modules over this nice stratification of what's called the mirror torus. So that's the theorem. So I drew this in examples. So if I take the line bundles O of -2, O of -1, and O on P2, what I end up getting is the projective modules. So I get this I get this homotopy path algebra we've been describing on this two-dimensional torus. I'll just draw it here like this, okay? And it has these relations, and there's a projective module for each of these vertices consisting of all, depending on your convention, all arrows, let's say, coming into the vertex, okay? So I think this is -2, -1, and 0. Maybe I'm not sure if I have, maybe going out of the vertex. So if I consider these three projective modules, they correspond to these three line bundles, okay? And as constructible sheaves on the torus, I look at the universal cover of the torus, which is R2, and I take the shriek forward of these different polytopes. And if you know some toric geometry, these are the polytopes corresponding to these line bundles. And these are the negative of the these are the negative polytopes corresponding to these negative interior of the polytopes corresponding to these line bundles. And those actually correspond to the three injective modules for the three vertexes. Also the strata, which looked like this, and this, and this, correspond to the simple modules over the side. So you can create some kind of dictionary, and you get this nice consequence that if you take any coherent sheaf on this toric variety, and if xi from this object, this sum of line bundles, remember was the sum, oops, some sum of line bundles, right? So if there's no higher x from these line bundles to your sheaf, right, then any projective resolution of this module, so my functor starts with the sheaf and outputs this module by assumption, okay, gives a resolution by line bundles of this coherent sheaf. So since we're projective, for example, you can take chi to be some very ample twist, and so you can always get a resolution by line bundles of your sheaf if you twist high enough. Okay, and you can get that resolution from using this non-commutative geometry. So here's a nice fact. If I take this bundle Thompson algebra, the projective dimension of it is actually just the dimension of the toric variety. Okay. So the homological dimension of this non-commutative ring is just the dimension of the toric variety. So this implies actually a nice statement in algebraic geometry, which is that for chi sufficiently large, f of chi has a resolution, but with line bundles in this finite set, and the length of this resolution is the toric variety. So we know, say from Grothendieck or something like that, that we have a resolution by vector bundles of this length, but we don't know its line bundles. So we're saying on a toric variety we can do better. We know its line bundles, and we know it's from a fixed finite set of line bundles. There's some bound on their magnitude and everything like that. So this was actually conjectured by Berkesh Herman Smith. And proven simultaneously and improved and done explicitly, actually, by Hanlon, Hicks, Lazarov, So I want to get more specific about what you can do to resolve specific coherent sheaves. So my setup's going to be the following. I'm going to take a sublattice n in n, obtained from some subspace. Okay, so if I looked at m prime n r, I'm going to take all the lattice points in some subspace. Okay, why do I do that? Well, then I get a new fan, which is just intersecting the fan for the toric variety with this sublattice, and I get a map of toric varieties. This is almost a closed embedding, except that you've taken a normalization because toric varieties are normal. And so you took you get actually a dense subtorus of your open dense. Sorry, you get a subtorus of your open dense subtorus. You take its closure and then you take its normalization. That's what this toric variety is. And so now you can take the push forward of the structure sheaf of this subvariety, okay? Essentially this subvariety. And we can say, okay, can we resolve this thing using topological methods, right? So using really what I think of as mirror symmetry or this sheaf, this homotopy path algebra philosophy. So, well, you get an exact sequence. And this is just the kernel. So this map of lattices induces a transpose map, right? And I'm just going to take the kernel, call it K. Okay. So that gives me a stratification of KR by K. So I had this original stratification of this torus. Now I have this subtorus of the mirror torus, KR by K. And this subtorus, I'll say on the next page, let me state the theorem and then I'll say why I do this. But the statement is that the Betti numbers of the minimal resolution of this sheaf, which is really this you can think of it as toric subvariety, okay, are given by sum of the compactly supported homology of the strata. So I've stratified this. These are just the new strata, which I'm just expanding out here. So you take the strata, you take the stratification of this subspace, and you compute the compactly supported homology of all of the strata, and you take the J part of that compactly supported homology and sum over those and call that beta J. Okay? And so the minimal resolution of this sheaf is actually, I know the numbers. Okay. I'm almost out of time, so I'm going to say this is just inspired by mirror symmetry. If I take this subvariety, so mirror symmetry says that the derived category of this toric variety is the Fukaya category of the cotangent bundle on that mirror torus, MR by M. And inside that, I have the cotangent bundle of this torus. And under mirror symmetry, this sheaf corresponds to the cotangent bundle of this thing. And so if I stratify it and resolve it, I end up resolving this thing. I'm out of time, so that's all I'm going to say about that. And I'll say one example. If I took just the identity point on the torus in P2, and I looked at this stratification, and now I computed the compactly supported homologies of these three things. Well, this only has compactly supported homology in degree 1. This only has, sorry, in degree 0. This only has compactly supported homology in degree 1, and it's 2-dimensional. And this only has top compactly supported homology. It's 1-dimensional. And so actually, the the algebraic Betti numbers of this resolution are actually topological Betti numbers given by compactly supported homologies of these strata. This is just the causal resolution of this plane. Okay, so I stop there.
Hey, thank you. Great. Are there any questions? So maybe I can start with a question. So in this theorem that you mentioned about this exact functor, sorry, a bit earlier. So if your T phi is actually a tilting bundle, then this becomes an equivalence.
Yes.
Yeah. Okay.
So that happens. Like for P2, this is an equivalence.
Okay.
But for say a Hertzsprung surface, it's not. It's just a fully faithful embedding. So part of what's happening is that in toric geometry, you have these birational transformations between different fan configurations on the set of rays. So if I give you a bunch of rays, there might be a bunch of fans that you can have with that same set of rays. In algebraic geometry, those lead to different birational models of this toric variety. Right? So, and if there's multiple, then what this theorem really says is that all of them can be thought of as different subcategories of the same fixed homotopy path algebra. And there's somehow their relationship to each other can be studied that way.
I see. But on the Hertzsprung surface, you also have a line bundle, which is a tilting bundle, right? Sorry, some
you
of them.
You do, but it's not this one. So this one has, like, if I took F2 or really Fn, right? This one has n+2 line bundles, and there's only 4. So there's a sub collection of this one, which is the tilting object. Okay, but this is bigger. Yeah.
Okay.
Yeah. So the fully faithful functor in that case is like, you could think of as, well, I can just include this as a sub algebra.
Yeah, I see.
Yeah.
Yeah, I was also wondering in
and also, sorry, one thing that's interesting is if you take on the Hertzsprung, if you took that those 4 objects and took the endomorphism algebra, the homological dimension is 3. So if you try to resolve your sheaves, you'll get longer resolutions using the usual tilting object.
I see.
You need, Go ahead.
Yeah, okay. Sorry, there's a comment by Alexei Bondar about conditions for this to be an equivalence.
Yeah, absolutely. Thank you. Thank you. Absolutely. And so if you have, so Alexei described exactly that if you have if all of your, so you can take all of your boundary divisors of your toric variety, and you can look at their intersection with curves. And so he described the following condition, which is that if all of the curves, if at most one curve intersects with -1, and the rest intersect positively, okay, of the toric curves, then this is an equivalence.
Right.
Yeah. So we called that bundle type.
Okay.
Right.
Yeah, I don't know. There any other questions? Otherwise, I'll keep going. So, yeah, I had one more question about your definition 3, about homotopy path algebra that comes from a stratification.
Uh-huh.
So is that any stratification, or do you need like a special kind of stratification? Is it? Yeah.
Yeah, so yeah, it's a little bit of a lie. Yeah, you're right. So it's what we called block stratifications.
Okay. So you have some condition on
Yeah, so there's some
the type
conditions
of,
on that
okay.
stratification.
Yeah.
I didn't want to get into it.
Yeah. Sure. Okay, great. Thanks. All right. Any other questions? That's not the case. Then let's thank David again.